discussing a body of work that's been carried out in a series of several papers with different subsets of collaborators that I've mentioned here. So let me start by explaining perhaps what is the basic idea or fact that makes it possible for there to be any connection between cluster algebras and scattering amplitudes. And this is simply the fact that for, well, let me write it like this. The kinematic domain for planar n equals 4 super-Yang-Mills theory. So this is the specific field theory whose scattering amplitudes I'll be talking about in the rest of this talk. The kinematic domain for this theory is an example of a space called a cluster Poisson variety. Okay, and let me explain what I mean by this. If you want to talk about a scattering amplitude of n particles in this theory, you need to specify n null vectors in Minkowski space that should add up to 0 due to overall momentum conservation. So you can parameterize, I'll just write it here, parameterize n particle massless scattering via momentum twistors each of which is some point in P3. I runs from 1 to n if you're interested in n particle scattering. Sorry, that's supposed to be a 3 there. Okay, so let's assemble the n homogeneous coordinates into a 4 by n matrix. Okay, so once again, each column here is a point in P3 representing the momentum twister associated to one of the scattering particles. Now, something that's unique, at least in four-dimensional field theories, something that's unique to this particular quantum field theory is a symmetry called dual conformal symmetry. Dual conformal symmetry acts on this matrix via left multiplication by, well, it doesn't matter if you call it SL4 or GL4 because these are all homogeneous coordinates. So let me go ahead and call it GL4. So the idea is if you have some scattering amplitude parameterized by some set of kinematics, then that scattering amplitude should be a function of this data that is invariant under left multiplication by GL4. So the kinematic domain for this theory is evidently then the space of such 4 by n matrices modulo this symmetry. Now, if we forget for a moment that each of these is a projective coordinate, and we read it sideways, then what we have here is a collection of, n planes and, 4 planes in n dimensions modded out by the action of GL4. That's what we call the Grassmannian. But then we have to recall that we also want to mod out by non-zero complex rescalings of each of these columns independently, because each of these is supposed to be standing for the homogeneous coordinate of some point in P3. So we have to mod out by C star, and here I have to put n minus 1 rather than n, because I already stole one of the factors, sort of the overall scaling, when I cheated and called that GL4 instead of SL4. So this manifold, or this variety, which I've been taught by Sasha Goncharov to call confen of P3, which is read as the configuration space of endpoints in P3. This is the kinematic domain for planar super-Yang-Mills theory in 4 dimensions.
So you also remove some bits of Grassmannian before quotient?
In what are you worried about?
Presumably no column of this matrix is allowed to be identically zero.
No column is allowed to be identically zero. That's right, yeah. So there is a rather delicate boundary structure here. So I should put a squiggle there, which means birational equivalence rather than exact equality. And there is a very delicate boundary structure to this space that does play an important role, but I won't say very much about it, but I'll allude to it. Right. Okay. Right, so the scattering amplitudes of this theory are going to be functions on this space. So what can we say about the nature of this space? Well, okay, it's a variety. Let's call it a variety. That's a relatively familiar word. Poisson means that this space has a natural Poisson structure. Okay, there's a natural Poisson structure on the Grassmannian, and it survives the quotienting, so that space has a natural Poisson structure on it. Let me mention here, just because this will come in handy later, the dimension of this space is 3 times n minus 5. So, in particular, this doesn't have to be an even integer, it can be odd, right? If n is an even integer, then that's odd. So this Poisson structure is necessarily degenerate, but that's fine. The last thing I should explain is what do we mean by the word cluster? So what that means is that there's a...
So did you tell us what the Poisson structure was?
Oh, I've said that it exists.
Okay, that's fine.
And
maybe you will, maybe you won't.
In a moment, I'll show you examples of I'll say, yeah, I'll get there in a moment.
Okay.
Yeah. Okay, so what does it mean to say that this is a cluster Poisson variety? It means that there's an object associated to this space called a cluster algebra. And you can think of a cluster algebra as an algebra generated by preferred sets of elements. So unfortunately I lost my notes, so I'm going off notes on the computer here. Yeah, so the idea is, what is a cluster algebra? Okay, and the simplest way to understand a cluster algebra is that you start with some set of generators, or let me say a set of coordinates. Let me do it more precise. You start with a set of coordinates that are log canonical with respect to the Poisson structure. So what I mean by that is you choose a collection of coordinates on your manifold. R is the dimension of the manifold, which in this case is 3 times n minus 5. And when I say you want your coordinates to be log canonical, what I mean is that the Poisson bracket of the logarithm of xi with xj is some integer valued antisymmetric matrix Bij. Let me write an example here. For example, okay, if we want n equals 6, and we want to talk about this cluster algebra, GR4, comma 6, I'll write a conf 6 is P3, we can choose the following coordinates. Okay, that's an example of a perfectly fine coordinate on this manifold. These brackets here refer to the determinant of the indicated columns. So 1, 4, 5, 6 means that you take columns 1, 4, 5, and 6 of this matrix and you calculate that minor. So that's obviously a perfectly fine SL4C invariant. But in order to make sure that you have a valid coordinate on this quotient space, you need to make sure that you have the same weight upstairs as downstairs for each of the 6 separate P3 homogeneous points. So 1 appears twice upstairs and twice downstairs, etc. So this thing respects the weight that you're modding out by. Now, for the case of n equals 6, this configuration space is a 3-dimensional manifold. So we need 3 coordinates to cover the manifold, at least the bulk of the manifold, modulo subtleties at the boundary. So we can define 2 other coordinates. So I'll define 2 others by just cycling each index here. 1 goes to 2, 2 goes to 3. Okay, you can see that if you cycle this by 3, you come back where you start from. So you only generate 2 new coordinates by cycling in that way. And you can check that log x1 log x2 equals 1, log x2 log x3 equals 1, and log, sorry, I'm running out of room here, log x1 log x2 equals 0.
But when you say you can check, you'd have to have told us what the class instruction was.
Yeah, so
So
it's,
sorry, also you mean log x1, log x3?
yes, thank you. Yes, and I will punt that question, except to say, with respect to the natural Poisson structure on the Grassmannian. So,
I'm still struggling.
okay, then let's discuss it later.
Okay.
So you know, the Grassmannian is a very symmetric space, and there's a natural Poisson structure on it. But I can write an explicit formula after the talk.
Okay. No, I'll be patient.
Except I wanted to say one more thing. Okay, this is just meant by way of an example. And one thing, let me point out that there are, given 6 points, 6 particles here, besides these 3 cross ratios, there are many other cross ratios I could have formed. Many other ways of writing a ratio of a product of brackets divided by another product of brackets. In fact, I think there are 90 different, if you do the combinatorics, there are 90 different cross ratios you can possibly form. Some of them are related to other ones by symbol transformations, but here I've selected 3 that are special. And one thing that's special about these 3 is that they're log canonical with respect to the natural Poisson bracket. For sure, there are other subsets of 3 that are log canonical, but this is one choice of coordinates that's log canonical. So working my way backwards on the blackboard here, what is a cluster algebra? Well, a cluster algebra can be understood by starting with some set of generators that are log canonical with respect to your Poisson bracket, and then there's a rule called the mutation rule for generating other sets of coordinates which are also log canonical with respect to the Poisson bracket. And I'll write the explicit mutation rule if I have it here in my notes. Yeah, here we go. Okay. do have it. Mutation on xk maps xi to 1 over xi if I equals k, and xi times 1 plus xk to the power bik if I is not equal to k. And this B matrix, I remind you, this is an integer valued anti-symmetric matrix that is the Poisson structure here. Okay, so the idea is there's a rule called the mutation rule, which lets you generate other sets of coordinates that are also log canonical with respect to the Poisson structure. And you can further mutate. Maybe that goes there, and this goes here, and also generate some other clusters, etc. Okay. So there's a large mathematical literature on cluster algebras. Let me just give you a brief indication why you might think that they might have anything to do with scattering amplitudes. Okay. This goes back to, well, let me introduce the simplest non-trivial cluster algebra, which is the A2 cluster algebra. And this can be understood as the algebra generated by only 2 variables, rather than 3, as in this example. So in particular, the A2 cluster algebra is not directly relevant to scattering amplitudes, though it appears as sub-algebras of the algebras that are relevant to amplitudes. And further coordinates generated by that rule. So if you work it out, you'll find that x3 is 1 plus x2 over x1. x4 is 1 plus x1 plus x2 over x1, x2. x5 is 1 plus x1 plus x1 over x2. And x6, amazingly, turns out to be x1 again. So this sequence is actually periodic. So this turns out to be a cluster algebra that's a finite rank. Here you have a cluster containing the variables x1 and x2. And what I've written here is the rule you get essentially after mutating on x1. And I won't draw everything here, but there are 5 different clusters, and then you come back where you started from. But anyway, the point I'm trying to make, the teaser I'm trying to make, is that there's an identity due to Abel, okay, in the 19th century. Now, he didn't know anything about cluster algebras, but he discovered a 5-term identity for the dilogarithm function. Let me remind you. Sorry. Log 1 minus t over t. He discovered a 5-term identity for the dilogarithm function where the arguments of the dilogarithm function are the negative of these 5 cluster coordinates. 1, 2, 3, 4, 5. So in quantum field theory and multi-loop calculations, as I'll review in just a moment, we often have dilogarithm functions and their generalizations appearing. So actually the first indication that there might be some natural overlap between the study of polylogarithm functions and between cluster algebras goes back over 150 years. Very interestingly, there's only one generalization, one non-trivial generalization of this identity that's known in the literature, and we stumbled across it a few years ago by accident. there exists a 40-term identity for the trilogarithm function involving a sum over cluster coordinates of the D4 algebra. That's not that's an interesting mathematical curiosity, but it's not particularly relevant for amplitudes. It rears its head, but I will not say more about that.
So I have some just zeroth order questions. So
Yeah.
are all the cluster algebras that are relevant for amplitudes kind of compact in the sense that?
No.
No.
Yeah, so I'll say more about that later. Right, so this is sort of a general picture, but for the cases that are of relevance to the scattering amplitudes, GR4, n, these are compact only if n is equal to 6 or 7. But as soon as n becomes 8 or higher, the sequence of mutations will never close.
Okay.
So you have infinitely many cluster coordinates.
And is there some sort of classification theorem for cluster algebras that are compact?
There's a classification theorem, absolutely.
Okay.
It's sort of an ADE type classification. Okay. All right. So this is all I'm going to say about cluster algebras, though there's much more. Now I want to introduce some mathematical machinery that we'll need. So I want to tell you what we've learned about the cluster structure of amplitudes. In order to do that, I need to explain some slightly more refined mathematical technology for dealing with these polylogarithm functions. To that end, we consider a generalized class of iterated integrals. Sorry, I lost my notes. I'm going off this computer. Right. Okay, yeah. Consider the iterated integrals of this form. And this is an interesting class of integrals because many of the simplest calculations of multi-loop amplitudes in various quantum field theories, not just in n equals 4, can be written in terms of this class of integrals. And so that makes them particularly useful and particularly well studied. And here you're integrating over the simplex a naught less than t1 less than t2 less than tk less than ak plus 1. Okay. Now, I've abused some notation here. This makes sense if all of these a parameters are on the real axis. In general, you can imagine that the a's are complex, are points in the complex plane, and you specify some path through the complex plane. Let's call that path gamma. It starts from a naught and ends at ak plus 1, and then this reflects the fact that you're supposed to do a contour integral where the points that you're integrating on are ordered along that path. But I hope that you forgive the slight abuse of notation. So this does implicitly depend also on a path that you're integrating along if the a's are general complex variables. Okay, so in fact, I said that many of the simplest non-trivial scattering amplitudes in a variety of theories can be written in terms of iterated integrals of this form. And that's almost a tautological statement because in a sense, the ones that are too complicated to be written in this form are too complicated for people to have explicitly evaluated. There are a few interesting and important counterexamples like the famous sunrise integral that can be expressed in terms of elliptic functions. But the vast majority of tractable amplitudes can be written in terms of iterated integrals of this form. And I should mention, of course, it was implicit, but I didn't say it explicitly. These generalize the polylogarithm functions, dk of z, which is defined as the integral dt over t dk minus 1 of c. Okay, so let's talk about this class of iterated integrals. The most important thing about them, as discovered by Goncharoff, is that they admit the structure of a Hopf algebra. Okay, so there exists a coproduct So if you consider the, I should have been a little bit more precise here. Let's first define the vector space of this of objects of this form. And moreover, we're not going to consider just a vector space, but we're going to turn it into an algebra, meaning we're going to allow you to take arbitrary linear combinations of arbitrary products of things of this form. So it's a vector space generated by products of these things. And it's a graded vector space because what we're going to do is we're going to say that an integral of this form has weight k. Okay. So k is simply the number of integrals in your iterated integral. Then if we multiply two things together, if they have weight, individually weight k1 and k2, then we say that their product has weight k1 plus k2. Okay, so when we consider the algebra generated by arbitrary products of these things, what we get is a weighted algebra, weighted by the weight k. And so let me add up here. Let A equal the algebra generated by such i's. So the vector space, you can think of it alternately as the vector space spanned by products of i's. Okay, I need that just because I realized that I hadn't defined that yet, and I'm going to use it in the next step. So there exists a coproduct that maps A into A tensor A, and it's compatible with multiplication. Oops. Okay, and it's co-associative. Okay. All right. Maybe I'm not going to define the, there's a beautiful formula for the coproduct of a general iterated integral of that form, but in the interest of saving time, I'll just mention what the coproduct looks like when acting on one of these functions. And I think that's actually correct, though I worry if I have my m and my k minus m mixed up here. Oh, and then there's the last term. No, that's right.
There's not a term with LIK tensor 1.
No, there's not, but I worry there's a term that's log to the k tensor 1.
So what are the primitive elements? Just logs?
Hold on just a second. No, it must be, you must be right. You must be right that there's a term. Oh, this is rather embarrassing. No, it doesn't look quite right to me.
I think if you had,
Someone here knows the answer. Can tell. Remind me.
it just seems like an ordinary logarithm should be a primitive element, and that means that you should
Yeah.
have one tensor log
Plus log tensor x.
1.
But that would come from, yeah, if you did, yeah, no, that's certainly the case. If you did,
You're not really anywhere like 20 minutes.
Various ways that might generalize.
Yeah.
okay. Since I'm being recorded, I'm going to erase this out of the
It's already recorded. You
Yeah. Okay. The important thing is that this lets you break down functions of this type into smaller pieces. So the iterated coproduct acting on functions of, so what I mean by that is delta to the power k acting on functions of weight k gives you something called the symbol. Of the function. So the idea is each time you act with the coproduct, you're breaking your function up into pieces. You start with something of weight k, and then you hit it with the coproduct. It becomes a linear combination of pairs of things whose weight add up to k. Then you hit it again, you hit it again. It doesn't matter where you hit it because of co-associativity. And if you hit it k times, you've broken your function up into just a sum of terms that are weight 1, tensor weight 1, etc., k times. So for example, delta squared, I should say delta k minus 1. Because, for example, no, it's safe to go all the way. Yeah. Delta squared Li 2 of z would give you minus oops, and I have that. Well, I didn't mean minus 1 there. Okay. In general, and I see now this is actually inconsistent with what I wrote on the previous board. So. Yeah, the order was wrong. Yeah. Okay. So this mathematical machinery is a useful tool because it lets you break down these functions into smaller pieces that are much more manageable. And one thing that's really nice about that is that these iterated integrals satisfy numerous functional identities. I mean, I already gave you a brief snippet of some of the simplest ones here, but of course they become vastly more complicated as you go to higher weight and as the arguments become more non-trivial functions of your underlying kinematic variables. But by working with the coproducts of functions, or even with their symbols, which is the fully iterated coproduct, you can break everything down into much more manageable pieces. Ultimately, the reason is because the functional identities for the logarithm are fully understood. It's just log of a times b is log of a plus log of b. And all of the functional identities for the higher polylogarithms can be sort of, once you chop them down, can be reduced to identities involving the logarithm.
So am I right that this coproduct, I can think of it as just all the different, summing over all the different ways I might break that big iterated integral into two separate iterated, breaking the chain somewhere in the middle.
That's right. So, yeah. tempting me to look at the clock and write the general formula.
There's no clock.
Yeah, later. Okay. This blackboard is all in the shade, I guess. All right. Now I'm going to introduce just one more bit of notation, and then we'll start getting to results. Okay. Sometimes it's useful not to work with this coproduct, but with something called the co-bracket. Okay, so I'm going to define a new space, which is the quotient of this, where we mod out by anything that's a product of functions of lower weight. So for example, Li2 of z plus log z log 1 minus z is equivalent to Li2 of z inside L. Okay, so here we just throw away, in this quotient space, we throw away anything that's a product of things of lower weight. The co-bracket is the coproduct restricted to this quotient space, and it satisfies an important identity. It satisfies delta squared equals 0. And that means this is the, in the sense of category theory, this is the co of the Jacobi identity. Okay. So if you just work it out, the fact that delta squared equals 0 is the co of the Jacobi identity. So we're talking about a Lie coalgebra here. So L has the structure of what's called the Lie coalgebra. Now, of course, this has nothing at all to do with whatever the physicists in the audience remember that in the back of their heads, we're talking about a supersymmetric gauge theory. So there's some gauge group floating around that doesn't play any apparent role because I'm talking about planar amplitudes and I've had all the color factors stripped off. And now the word Lie algebra, or at least Lie coalgebra, is rearing its head again. This appears to be some completely other kind of structure whose implications for the structure of scattering amplitudes sounds like it ought to be important, but is definitely not yet fully understood.
So that dot between the A and the A in the quotient for L is sort of symmetrizing. I mean, that should be a symmetric product, should it? It's A over A symmetrized with A, is it?
Well, I mean the product set. Anything in A? No, it doesn't have to be symmetric.
Oh, I see. I just thought it might be a skewing operation. It's not really a skewing. Does it skew the symbol?
Oh, well, at weight 2, all it does is, at weight 2, that you can throw away products by skewing the symbol. Yeah,
Right.
that's true.
Oh, I see. But okay, but I should think of it as something a bit more. Okay.
Because at weight 2, anything that has a symmetric symbol can be written as a product.
Mm.
With a physicist hat on, it's always tempted to think of these iterated integrals as some sort of Wilson line.
Yeah.
And I understand it's got nothing to do with the gauge group of the Yang-Mills.
No, I don't think
It's
so.
anything to do with the gauge group that one gets
From the Wilson loop picture.
from that.
No, again, I
I
don't.
don't mean the Wilson. You understand what I mean, right? Just that iterated.
Just that iterated integral is literally
It is
calculating some kind of
whether
Wilson
whether
line.
gauge fields have been replaced by those.
Yeah, I don't know. That's an interesting question. Okay, finally, I'm ready to make some statements. Okay, so wait. For example, the next few statements I'm going to make are specific to two-loop amplitudes. So at weight 4, This is relevant to two-loop amplitudes. So in general, in 4 dimensions, the weight of a function is going to be twice the number of loops. Okay, so once I get to the top board, I'm going to make some statements about two-loop amplitudes. So we're talking about weight 4. Delta has 2 components. It has a 2,2 component and a 3,1 component. Remember, it's erased now, but in general, the coproduct gives you a linear combination of terms with different weights adding up to the total. Well, there are 2 ways you can have there are 2 non-trivial ways you can have something add up to 4, 2,2 or 3,1.
You don't count 1,3 separately.
We don't, because that turns out to be equivalent in this quotient space to 1,3. If we were talking about the coproduct delta, yes, then 1,3 and 3,1 would be different. But here in this quotient space, 1,3 and 3,1 are isomorphic. And there's no such thing as 0,4 or 4,0 because that's sort of trivial in this quotient space. That would correspond to a sort of by definition. Okay, now the statement. At 2 loops, we have tons of data, not thanks to the LHC, but thanks to Simon Carantois, who I'm sorry, it's not misspelled, though maybe my handwriting is poor.
So it's cheaper to build.
Oh yeah, cheaper to yeah, who in 2011 calculated the symbol of, well, actually he did more than that. He calculated the full differential, which is even more information. But he calculated the symbol of all MHV two-loop amplitudes. For all n. So from that information, we were able to compute these coproduct, or I should be precise and call these co-bracket components. And what we observed, and I'll phrase this here as a phenomenological observation, because we have no understanding of why this ought to be the case. One, the 2,2 co-bracket component can always be written as a linear combination of things of the form Li2 and up here there really is a wedge because in the quotient space. Okay, so far there's not much of a surprise here because I didn't mention it, but it is a theorem. Well, you can just evaluate that iterated integral explicitly. Any function of weight 2 can be written as a linear combination of the dialog. The dialog is the only function at weight 2, if you will. So of course, the 2,2 component of the co-bracket can always be written as Li2 of something, wedge Li2 of something else. The punchline here, the highly non-trivial thing, is that where the xi's, xi and xj, are cluster coordinates, or so-called Falk-Gonchoroff coordinates, on GR4, n with Poisson bracket 0. Okay, so just to iterate how surprising this is, starting at 8 points, so this is true for any n, starting at 8 points, there are infinitely many cluster variables. They get more and more complicated. Of course, only a finite number of them actually show up in Simon's result. But those that do always come in pairs with Poisson bracket 0. Let me say one more thing that, I'll postpone that thought. Punchline number 2 is that the 3,1 component is similarly the 3 minus xi with log xj you always get pairs with Poisson bracket 1. Now let me make a few comments about this to try to tell you that this is surprising. So I drew this picture before where you have different clusters connected to each other by mutation. Now, it's only within each cluster that the variables it's only within each cluster that the Poisson bracket between any pair of variables will turn out to be an integer. If you try to compute the Poisson bracket of the log of some variable here with some variable over there in some distant cluster, it won't come out to be an integer. It'll come out to be some non-trivial function on your manifold. It won't even be constant. It'll be garbage.
That's a generic statement, or that's always true?
That's always true. So another way to say it is that if you have two variables and you've checked that the Poisson bracket of their logarithms is an integer, then there exists some cluster where they both live together. Now, for the case of 7 particles, well, for the case of 6 particles, there are 14 different clusters. And this forms a beautiful combinatorial picture called the K5 associahedron. For n equals 7, there are 833 different clusters. Starting at n equals 8, there are infinitely many different clusters. So if you will, the chance that you pick 2 random variables and there happens to exist some cluster where both of them live together is vanishingly small.
So this is also true when it vanishes.
That's right. So if you have
two, still implies
0 is an integer.
Yeah.
So
okay.
let me say that explicitly.
Okay.
If you have 2 variables that Poisson commute, then it's guaranteed there somewhere exists some cluster that contains those 2 variables. So this is a very rare thing. If you look at all possible weight 4 functions, almost none of them have these properties. And in fact, in a paper with John Golden, we showed that if you knew nothing else about scattering amplitudes, but just asked the question, let's try to look for or categorize the space of weight 4 functions that satisfy these properties for some given cluster algebra. Well, together with a few modest inputs from physics, for example, that the scattering amplitude should be dihedral invariant, together with some statement about the appropriate branch cuts, I'll say more about this in a moment, these constraints uniquely determine the two-loop MHV amplitudes modulo products of things of lower weight, because all of this statement is still at the level of the quotient space where we've modded out by things of lower weight. Now, physicists always ask me, oh, aren't you bothered by modding out by things of lower weight? And yes, of course, it's true. You know, if you're designing an experiment to measure something, you need to know if you've got, if you're designing something to measure an actual number, you need to know if you've got that term there or if you've got a 1/7 there. But from the point of view of understanding the mathematical structure, this is still quite a profound statement. And also, this limitation is not, in practical applications, it's not as limiting as it might seem, because it's often the case that you can reverse engineer these sort of subleading functional terms by relatively simple considerations, such as by looking at collinear limits, at how amplitudes should behave as two momenta become parallel. Okay, so this is an example of what we call the cluster bootstrap, using things that we know or hypothesize should be true about scattering amplitudes and trying to construct formulas for scattering amplitudes from that information. And let me again emphasize that this is completely a phenomenological observation. We don't have understanding why it should be true. We also don't have any understanding how this statement generalizes to higher weight. And I'll just say a few more words about that in my last 5 minutes. Here we were really aided by the fact that we had this wealth of data to analyze. Okay, if you want to go to higher weight, that means you need to go to 3-loop amplitudes or higher. And there's precious little information available in the literature on 3-loop amplitudes. Lance Vixen and his collaborators have done impressive work pushing forward to higher loop, but only for 6-particle amplitudes. That's not yet enough information to be able to even guess at what the analogs of these kinds of statements might be at higher loop. So another thing that I've been pursuing with some collaborators is a weaker form of the bootstrap. A weaker form of the bootstrap that only uses the hypothesis that all n equals 6 and 7 point amplitudes have symbols. So here we're not putting in information about the coproduct, have symbols that can be written in terms of cluster coordinates. Okay. And I'll pause here before continuing this thread. I'll mention again that we know that for n greater than 7, there exists an infinite number of cluster coordinates for the algebra GR4, n. Of course, we know that at any finite loop order, only finitely many of them will possibly appear, certainly in MHV amplitudes. But we don't yet have any mathematical understanding of what is special about the subset that does appear. For example, we can look at Simone's result and we can see which ones appear at 2 loops. But it's an open question whether the same subset suffices at 3 loops or whether the set of cluster coordinates that you need grows with loop order, and if so, how? So that's a very interesting open question. So let me just restrain my comments now to 6 and 7 point amplitudes where the number of cluster coordinates is finite. So in particular, the space of such objects is finite. So for example, let's look at weight 6 for n equals 7. Weight 6 means we're talking about a 3-loop amplitude. Suppose you wanted to study the 3-loop 7-particle amplitude. And suppose you were only willing to hypothesize one thing, which is that the symbol should be written in terms of cluster coordinates. Well, there are 42 cluster coordinates. this is a lie. There are 42 multiplicatively independent. That's all we need. That's all we need if we're putting these inside the entries of a symbol, because symbol entries satisfy logarithm-like identities. You can expand out products. Log A times B is log A plus B. So you don't need all cluster coordinates, you just need some multiplicatively independent basis, and that basis has size 42 for GR4, 7. So what you do is you make an ansatz. So, in other words, the 3-loop MHV amplitude is some vector in the 42 to the power 6 dimensional space. In other words, what I'm saying is suppose we make an ansatz that our scattering amplitude should be a linear combination with some rational numbers as coefficients. And then here's a weight 6 symbol whose arguments are some of these 42 cluster coordinates. So all we have to do is find some vector, or actually some ray, since this method won't determine the overall normalization, in this vector space of size 42 to the 6th, which is large, I grant, but still manageable by sufficiently powerful computers. If you specify that the function should be finite in the collinear limit, that means as you take two of the momenta of two cyclically adjacent particles to be parallel, the scattering amplitude should be finite, and that the function must have only physical branch points That's a condition about what appears here in the first entry of a symbol. If you go back to the definition of the symbol, you can quickly see that a function with this symbol will have branch points anytime the first entry here is equal to 0. So physics places strong constraints on where the locations of branch points of scattering amplitudes may be, so that becomes a condition on the first entry here. And then there's also one tiny little constraint from supersymmetry on the final entry. Okay, I won't explain that in more detail since I'm already over time. But the upshot is that there's a unique solution. So in this vector space of size 42 to the 6th, there's a unique linear combination, well, unique up to an overall scale, which I say again, this method doesn't determine. There's a unique function that's finite in the collinear limit, only has physical branch points, and satisfies a certain constraint on the last entry condition coming from supersymmetry. So this is another example of what we call the bootstrap, where we're using what we know is true or what we suspect is true about amplitudes. And once again, let me emphasize that nobody has proven that we believe it's true. It's supported by all available evidence to date, but nobody has proven the hypothesis that 6 or 7 point amplitudes should have symbols entirely expressible in terms of cluster coordinates. We believe it's true to all loop order, and so what this research program is amounting to is let's start with the hypothesis and see if it leads to any contradictions. So far, it doesn't seem to lead to any contradictions. It seems to allow us to compute, and again, I should say, we haven't been able to check this computation against anything else, so it's standing there in the literature. If someone wants to go evaluate all 3-loop Feynman diagrams contributing to this and check our calculation, that would be an important application of the scientific method, reproducibility.
Well, don't the integrability guys have something on this? That's Pedro and friends.
Yeah, that's right. So BSV, Basso, Sever, and Vieira have an approach for studying these scattering amplitudes from an orthogonal point of view. And so they can do cross checks on the expansion of this thing around the collinear limit. And I don't know how far that
So
check
they
has
don't
gone.
get all 3 parameters.
They can't go, I mean,
They don't get.
I don't know if they can write an explicit formula. So just to emphasize that our expansion here is in the 't Hooft parameter, so we do things 1 loop at a time. Theirs expansion is to all loop order, but there's an expansion around the collinear limit.
Oh, I see.
So there's definitely cross checks between the two approaches.
And when Lance was talking about these things, he was saying that you actually need to use data from their from their expansions, whereas
That's
here
right.
it doesn't seem to.
That's right. So here, so Lance and his collaborators, when they do the bootstrap for 6 points, they do use a lot of input from the BSV OPE analysis. This is rather magical that it turned out not to be the case, and I can only say it just, for reasons that we don't understand yet, the bootstrap for 7 particles appears much more constraining than that for 6 particles.
Oh, I see. So there's something degenerating in 6 particles.
When you do this procedure at 6 particles, you're still left here not with a unique solution, but with a hundreds or 1,000 parameter family of solutions that you can then fix by comparing to BSV. But for some reason, the constraints from GR4,7 are much stronger than they are for GR3,7. So in fact, if you wanted to compute the 3-loop 6-particle amplitude, which Lance and his friends did maybe 5 years ago already, now we know that the conceptually simplest way to do it is to first compute this thing and then take its collinear limit.
So is this potentially overdetermined? I mean, so you've got many more conditions.
There are many more
Which
conditions.
includes, power
For
6.
example, dihedral symmetry. It didn't have to happen that this thing is dihedral.
It would already be determined before dihedral.
So for example, Lance and friends, they have to input dihedral symmetry.
Right.
But here it's an output, okay? If there's a unique solution, it has to be a singlet under all possible discrete symmetries, in particular under parity, and under the dihedral group. But that wasn't an input.
Okay.
It's not secretly there in only physical branch points.
No, it's not, because it's easy to have a function that only has a branch point in one physical channel. This has to be cyclically invariant and have branch. So the physical branch points is a statement that the first entry of the symbol can only involve 4 brackets of this form for various I and j. But there's no reason that imposes dihedral symmetry. And the last entry condition is a statement that only these can appear in the last entry. So we've been continuing to work on the bootstrap. Actually, there's news just this morning that we finally have a basis for all of the weight 7 functions for the heptagon. And that means I suspect that we'll know the 4-loop amplitude very soon, like days or weeks. But okay, I'm already over time, so thank you for your patience. Yeah.
I have n questions.
N is large? Okay, good. I'll turn this way so if people want to exit, I won't.
Yeah, right. Maybe I should do the same. Is the hope that if you go to more particles, n equals 8, etc., where I'm not sure whether they're all multiplically independent, but you said there are infinitely many cluster coordinates.
That's right. But only a finite subset will appear at any finite order. let me tell you what my hope
But it
is.
doesn't look like you have an infinite set of constraints from those ones you wrote down.
Right, that's right. So we desperately need somehow on this set of infinitely many coordinates, there's some kind of gradation that hopefully it's something that's familiar to the mathematicians or makes sense to the mathematicians, but in physics language, what it would be is, oh, aha, this is the subset that can appear at 2 loops, this larger subset can appear at 3 loops, and that's completely unknown. But let me make one broad comment about the hope. One of the things that Lance and his friends are not inputting into their analysis is that, so they call these things hexagon functions, functions that are built from the symbol alphabet for GR4, 6. Well, not every hexagon function is the collinear limit of some heptagon function. Okay? You can write down hexagon functions that satisfy all these nice constraints, but there does not exist any 7-particle function which in the collinear limit goes down to that. So I think the way to think about it is that there's this infinite tower of constraints. If this is the space of all hexagon functions, and here's the space of all heptagon functions at a given weight, let's say at weight 7 or 8 or 9, whatever, you can look at the image of this under collinear limits, and it's some subset. Okay, then of course, you could imagine looking at octagon functions, and they have some image under the collinear limit, etc. So ultimately, I mean, whenever you're doing bootstrap, we have a doubly infinite set of functions labeled by loop order, labeled by n, and of course, I didn't mention it, but also labeled by MHV degree. And these functions are all related to each other in some very complicated ways, but the ultimate hope of the bootstrap approach is that there will sort of only be one unique set of functions that satisfies this whole, it's like a house of cards, that, you know, there will only be one set of functions that satisfy the whole list of constraints. And finding that set of functions, or how to characterize it, is the goal of this bootstrap.
But it could be empty. I mean, you know, if this elliptic
Well,
purported counterexample of
Well-
Neiman friends is actually really true, then it's empty, isn't it?
Well, no, it's not empty because we know these scattering amplitudes exist and we can compute them in some examples. But yes, I
mean, there's no guarantee that it's polylog. I mean,
No,
that's the whole point of the point.
oh, absolutely, right. So this kind of picture might exist for MHV amplitudes and for NMHV amplitudes, which are believed to be polylogarithmic to all loop order. But as Lionel was referring to, we know that once you get to sufficiently high non-MHV degree, we know there exist amplitudes that are outside this whole realm of generalized polylogarithms.
Well, I mean, and no is a bit of a strong word.
I think we know.
Oh, you think we do?
I'm confident.
Okay. I wasn't
Yeah.
entirely clear. I
Yeah.
trusted their argument.
Yeah, I trust it.
You do?
So,
Okay,
yeah,
okay.
I trust
You're more
it.
expert than me.
Yeah.
so
So here we're just trying to bite off a piece of the pie.
I see. So for MHV and NMHV, you think this
will work.
This should
Yeah.
work.
I mean, it might prove too difficult to carry out, but we believe that MHV and NMHV amplitudes will be polylogarithmic to all loop order. Now, once you go to sufficiently non-MHV amplitudes, you get examples of elliptic functions. And so by way of speculation, I'll just tell you what I told you after lunch the other day, which is that it's an intriguing coincidence that the only example of elliptic type multi-loop integrals that have been explicitly evaluated in the literature is the famous sunrise integral. There are some papers by Bloch and Van Hove, and I think also by Weinzierl. But the interesting thing, this particular example is not something that appears directly in Super-Yang-Mills theory, but they studied it, and the interesting thing about their result is that they can write it as an infinite linear combination of dilogues.
Oh yes.
Okay, so isn't it curious that elliptic integrals are also starting to appear exactly where we have infinitely many cluster coordinates available? So if you're the kind of person who doesn't believe there are coincidences in n=4 super Yang-Mills theory, you might be tempted to speculate that there's some connection between these two infinities. But this is really out in the realm of rampant speculation.
Can you go back to the beginning? So there's a simpler situation, which I think I understand, and I want to know whether this is supposed to be analogous with what I'm supposed to think of the other way. And the simpler situation is world sheet for string theory. Suppose I'm computing an endpoint correlation function on a Riemann sphere in strings. So I can think of these endpoints as described, I can think that I'm in some open set of G2n, mod out by some scalings, or I'm supposed to mod it out already by GL2, and I should probably remove diagonals on the world sheet where my mark points collide.
Yeah.
Now, turns out that's not really the right, there's a naive compactification of that space, which is just to put those diagonals back in, but that's not really the right one.
Yeah.
The right one is the Lee-Mumford one. And it's right in the sense that the actual string theory amplitude has singularities and monodromies around the boundaries of the Lee-Mumfords. Is the claim that these Poisson, these cluster Poisson varieties are A, compact,
Yes.
or they have a compactification,
They have a
and that
compact.
this is actually the right compactification in the sense that these amplitudes have monodromy and singularities
Yes.
around the boundaries of this cluster variety.
All,
not
yeah,
around the-
there is a natural, all evidence available to date suggests that that's true. And yeah,
but,
so
but not around perhaps all of the boundaries of this space, because a lot of the cluster coordinates seem to be irrelevant. And that, again, is some sort of reality structure coming in the same way as I could put a reality structure on the Lee-Mumford moduli space that says that amounts to working with open strings, so that my points are ordered around the boundary of a disk, and that throws away all the sort of non-ordered boundary components or incompatible. Something similar may be going on here, that only some subset of all the many boundary components you've got in this Poisson variety are really playing a role.
that the last statement, that must be true, but we don't understand
What's the condition?
what's the condition. Like, for example, I mean, you can take this picture, and we had undergrads who wrote a Mathematica program to draw a picture of this polytope with 803 vertices, showing the mutation graph for for the n=7 cluster algebra, and then there's a sense in which that polytope, I won't explain this, but that polytope literally represents the compactification of the space. And
Like the associahedron that we're talking about.
yeah, it's a generalized associahedron. And so then we can ask the question, okay, let's look at the actual two-loop amplitude, and let's look okay, so it has a 2, 2 coproduct component that can be written as a linear combination of 42 terms. And as I've said, in each term, you've got a pair of coordinates with Poisson bracket 0. So let's look in this object, where are those 42 pairs with Poisson bracket 0? Oh, there's one here and one there, and one. But I don't know the pattern I don't know what's special about those boundary components. So.
Is this right that each cluster provide good coordinates in the neighborhood of some boundaries? So for example, the x's can probably go to 1 because you want log x.
We usually work in normalizations where the natural range is 0 to infinity. And
open though, you don't want it to go to 0.
yeah, that's right. So I can do the case of n=6 explicitly. There's this famous 1, 2, 3. Okay, wait. There's a picture here which is a cube with the corner shaved off. Okay, and I haven't completely drawn it, but it has 14 vertices. Each vertex here represents a cluster. So if the coordinates of this cluster are x1, x2, and x3, then the idea is that as these, so in this coordinate system, that's the point 0, 0, 0. And as you go out to infinity, you push up against the other sides of this. This would be a coordinate system where if this is the edge where you mutate on x1, the first coordinate here is 1 over x1, because that's x1 equals infinity, or 1 over x1 being 0. And then there's some other coordinates here. So each of the boundary components, so the compactification, well, the way to think about it is as a blow-up. You blow up each of these boundary components, and they're not all visible in every different coordinate system. But for every one of them, for every boundary component, there is some coordinate system where you can see the whole extent of it.
And presumably all those boundaries correspond to some sort of special configuration of the points in the original.
Well, some of them are special, like
The cross ratios.
like these 3 lines are collinear lines. So the point is, some of these boundaries are physically relevant, have physical interpretations like collinear limits, but other ones of these are not physically relevant. And in fact, it's a highly non-trivial constraint that you should have a function that has singular behavior only where you are supposed to have singular behavior, and non-singular behavior where you're not supposed to have singular
But
behavior.
they all mean that some combination of cross ratios is doing
Something weird, like going,
Which
yeah.
means that some, whether it's compatible with some physics intuitions doesn't matter.
Right,
Some-
right,
some set of
but
these
some
things
cross
doing
ratio is going to
something
0,
which
1,
are-
or infinity, right?
Is it always, do they always show just linear relations? I mean, if you had 6 points and they happen to lie in a quadric or something like that.
No, they can be more complicated.
Oh, they can?
I think in higher, maybe not in n equals 6, but for n equals 7, yeah, absolutely.
Is there any way from that side to see why you suddenly get infinitely many when n goes to 8? Suddenly there are all sorts of more weird things.
Yeah, I don't know how to see that intuitively.
So should we applaud?
Yeah, if the rest of the audience
Sorry,
doesn't
sorry.
share his
Sorry,
fascination,
yeah.
their eyes are all glazed over.
I still want to know what the Pascal structure is.
Oh, okay, yeah, yeah.